Hey everyone, let's dive right into this explainer and upgrade our understanding of how real-world objects actually move. Up to this point, if you've been studying basic mechanics, you've kind of been treating cars, planets, and people as if they were just infinitely small dots sliding around on a frictionless page. It's a great starting point, but let's be honest, it's not reality. Today, we're focusing squarely on explaining the chapter where things get wonderfully real and a whole lot more complicated: systems of particles and rotational motion. Here is our roadmap for today to transition our thinking from simple moving dots to complex, spinning realities. We're going to hit moving beyond point particles, the center of mass, translation versus rotation, torque and vector products, the moment of inertia, and finally, conserving angular momentum. Let's get into it. Section 1. Moving beyond point particles. So up until now, we've treated almost everything in physics like an infinitely small point mass. But, just look around you. Any real body we encounter has a finite size. We absolutely need to address the fact that real objects have shape, they take up space, and most importantly, they tumble and spin. Toss a baseball across a field, and it doesn't just glide cleanly through the air, it rotates. That idealized model of a single, dimensionless particle is just completely inadequate for capturing this kind of dynamic, real-world behavior. To handle this complexity without losing our minds, we introduce a brilliant shortcut: the rigid body. It's a foundational model where we just assume an idealized extended body has a perfectly definite and unchanging shape. We pretend the distances between all the particles inside it remain perfectly constant. Now, is anything in the real world perfectly rigid in the absolute strictest sense? No, of course not. Everything deforms a little bit under force. But for solid stuff like metal wheels or steel beams, those deformations are so microscopic we can just entirely ignore them. Treating them as one unified, rigid shape gives us a beautifully workable way to calculate their motion. Moving right along to Section 2, the center of mass. Okay, so even though we just established that real objects aren't single points, we can actually still use a lot of our classic math tricks if we simply find the object's sweet spot. The center of mass is this brilliant workaround. It essentially lets us take a messy, tumbling system of particles and track its overall translational motion as if its entire mass were concentrated at one single predictable point. It's literally the bridge between the simple physics we know and the complex realities we're trying to figure out. You can see this beautifully illustrated in a binary star system. You've got these two distinct, massive stars whipping around each other in these incredibly complex, wobbly paths. If you try to calculate the trajectory of every single particle in that system, it's an absolute mathematical nightmare. But there's a specific balance point between them, their center of mass. Even while those stars intensely orbit each other, that center of mass glides forward in a perfectly smooth, uniform, straight line. By separating that steady motion from all the chaotic internal spinning, we can effortlessly solve problems that would otherwise be impossible. Section 3. Translation versus rotation. Now, we really need to look at the stark contrast between these two fundamental types of motion. On one hand, you have pure translational motion. Picture a wooden block sliding perfectly straight down a smooth ramp. Every single particle in that block is moving together in the exact same direction, with the exact same velocity. It moves as a unified whole. But contrast that with rotation about a fixed axis, like a spinning ceiling fan. The body as a whole isn't traveling across the room, right? Instead, every single particle inside that body is tracing its own perfect circle around a fixed central line. Which brings us to Section 4, torque and vector products. To truly wrap our heads around spinning, we have to step into the rotational mirror universe and look at the vector product. It's a mathematical tool that gives us a completely new direction, one perfectly perpendicular to the forces we apply. If you literally hold up your right hand right now and physically curl your fingers in the direction an object is rotating, your extended thumb points firmly in the direction of the angular vector running right along the axis. It's a remarkably simple geometric trick to map out totally invisible forces. And that brings us to a massively important concept: torque. Sometimes we call it the moment of force. Just as linear force pushes an object in a straight line, torque is its rotational twin. It's what causes an object to start spinning or changes how fast it's spinning. It's defined as the vector product of the radius and the force applied. The formula is beautifully intuitive. Push harder or push further away from the pivot point, and you generate significantly more torque. Imagine you're opening a really stubborn jar. Your thumb pushes one way on the rim, and your index finger pulls the exact opposite way. You're applying equal and opposite forces, but you aren't doing it to slide the jar across the kitchen counter, you're doing it to spin the lid. In physics, this is mathematically called a couple. Your fingers create a couple, which generates the exact torque needed to pop that lid open. And honestly, the exact same invisible mechanism happens on a planetary scale when the Earth's magnetic field grabs the opposite poles of a tiny compass needle, creating a couple that torques the needle to firmly point north. Same exact physics. Let's keep building our rotational cheat sheet in Section 5, the moment of inertia. So if torque is the twin of force, what on earth is the rotational analog of mass? We know that in basic linear motion, mass resists a change in speed. A heavy boulder is incredibly hard to push, right? But for spinning objects, just knowing the total weight isn't enough anymore. We need a totally new property to tell us how hard it is to get a heavy, extended object spinning in the first place. And here is your ultimate cheat sheet for that. It maps exactly how linear concepts translate directly into the rotational world. For speed, standard velocity simply becomes angular velocity. For a push or pull, force becomes torque. And mass, that translates to something called the moment of inertia. And here's the kicker. The moment of inertia doesn't just care about how much mass you have. It cares absolutely crucially about exactly where that mass is distributed relative to the axis of rotation. A solid dense cylinder and a wide hollow ring might weigh the exact same amount on a scale, but because their mass is distributed differently, they're going to resist spinning in completely different ways. And for our grand finale, Section 6, Conserving Angular Momentum. Let's tie all of these mechanics together with the spectacular conservation of angular momentum. Picture yourself sitting on a free-spinning swivel chair with your arms stretched way out to your sides. A friend gives you a really hard spin. You've got a certain amount of angular momentum now. Okay, now violently pull your arms tightly into your chest. Without anyone pushing you again, you are suddenly going to spin so much faster. Your body just practically demonstrated this law of physics in real time. But why exactly did that happen? It all comes down to this core mathematical rule. As long as there's no outside torque messing with you, like annoying friction from the floor, your total angular momentum, represented by L, has to stay exactly the same. When you pulled your arms in, you drastically changed your mass distribution, which shrunk your moment of inertia, or I. Because the total equation mathematically has to remain constant, if I goes down, your angular velocity, your spin speed, or omega, literally has to instantly increase to compensate. And this isn't just some fun parlor trick with an office chair. It's the exact same undeniable physics an acrobat employs when they tuck their knees tightly in to nail a rapid mid-air flip. And remarkably, it's the very same principle keeping massive planets locked in their sweeping orbital dances across the galaxy. As we wrap up this explainer, I really hope you look at the spinning, tumbling world around you with a completely upgraded set of eyes. Look for that hidden center of mass. Look for the invisible torque applying a twist. From acrobats doing flips to planets orbiting the sun, where else will you spot angular momentum secretly at play in our world? Thanks for joining me on this deep dive. Keep observing and keep questioning exactly how our universe moves.